Liverpool. He holds a PhD from TU Wien, where he has completed a postdoctoral fellow as well. His research focuses on propositional SAT and its generalization, such as quantified Boolean formulae. Today, he's going to talk about the introduction of QBF solving. So, stage is yours, Rich.
Thanks, Subhajit. Great to be here and follow Alex's tutorial from the morning. So I'm going to talk about a generalization of propositional logic called quantified Boolean formulas and how to reason with and reason about these formulas. So first of all, why would we even want to do this when SAT solvers are so incredibly efficient and fast? Well, a very banal reason is that there are certain problems for which you simply cannot generate a succinct one-shot monolithic SAT encoding. For instance, let's take a scenario where we have a circuit here with a number of inputs, outputs, and a black box of control signals here that we would like to synthesize. And we have a Boolean specification. So it's a propositional formula that speaks about these input variables, which are Boolean, the control signals, which are Boolean, and the output signals that are Boolean. And now, how could we use SAT to generate a controller that, given the inputs, generates outputs that satisfy the specification? Well, we could look at the first assignment of our input variables. Let's call that tau1. And then, because our control signals will generally depend on this input assignment, can generate propositional variables, one for each control signal, that we sort of mark with the, oh, it's okay. Okay, great. So we're trying to synthesize a controller here with Boolean inputs, outputs, and we want to synthesize the control signals depending on the input signals, right? So we introduce a set of propositional variables, one for each control signal, and this particular input assignment, right? Maybe it's the all zero assignment that we start with. And now, oh, now it's not focused, I guess. All right, okay. So we have our control signals, which depend on the input assignment, and the outputs will depend on the input assignment as well, right? So what we could do to generate our first part of the SAT encoding is take our specification phi and then replace, well, the input variables with the input assignment tau1, and replace the control variable c with this copy c tau1, which is for the control signals under the assignment tau1, and then also replace the output variables or substitute these variables for our output variables, right? And so that would, what that formula says is for under the input assignment tau1, we want to find values for c tau1 and for o tau1 that satisfy our specification, right? Now that's for the first input assignment. And there, in general, we'll have multiple input. Well, we'll have at least two input assignments. But yeah, so we'll have another one like tau2. And we could do the same thing now for the second assignment of the input variables. That is, create a copy of the control signal variables, create a copy of the output variables, plug that into our specification together with the second input assignment, and add that conjunctively to our SAT encoding, right? Which says, okay, under assignment tau2, we want to find values for the control signals and the output variables and the outputs so that our specification is satisfied. Okay, and so we continue with this, and it is clear that if we want to generate like the single monolithic SAT encodings, we're going to require 2 to the n copies of our specification if n is the number of input variables, right? Because we have that many assignments. Of course, that is an extremely naive way of doing this. In practice, you might still want to use SAT in a clever way to solve that problem, but that's just to say you can't, or it's infeasible if you have a large enough number of input variables here to simply generate this one-shot SAT encoder. So what we would like to be able to do here, just intuitively, is quantify over all of the input assignments if we wanted a succinct encoding of what we would like to achieve, and say something to the effect of, for all assignments of our input signals, there should exist, or we want, an assignment of the control variables and outputs such that the specification is met. Okay? So to get a succinct encoding of this kind of problem, we want quantifiers in our logic. And in general, the question here is, which logic should we use for automated reasoning? We've seen propositional logic. Now that we want quantifiers, we could go all the way to first order logic. But we have to trade off efficiency of reasoning and succinctness of our encodings in some sense. So propositional logic, as we have seen, or as Alex has mentioned, very efficient, but arguably not very succinct compared to something like first order logic. And then first order logic, okay, I don't want to step on anybody's toes. I don't think any first order people are here, but like generally speaking, of course, first order reasoning is hard. So first order solvers, theorem provers, probably a bit less efficient, but you can have these extremely succinct encodings, right? SAT is NP complete. First order logic in general is undecidable, which in practice also means that sometimes your solvers won't, or perhaps it's more likely in practice than for SAT that your solver is going to run indefinitely and not give you an answer in reasonable time. And quantified Boolean formulas are an attempt to sort of approach something more expressive from the propositional level. And as we'll see, reasoning with quantified Boolean formulas is a p-space complete problem. Okay, so I think at the moment, propositional logic gives you the best balance in many cases between succinctness of your encodings and efficiency of reasoning. But I hope that by improving QBF solvers, you can sort of move the trade-off for QBF closer to the trade-off for propositional logic. Okay, let me start with some basics. Just a brief slide on the syntax of quantified Boolean formulas. Well, a quantified Boolean formula is essentially, yes? Sorry? Well, I mean, just like in the example that we had on the slide, there is just you can't just, as a user, right? You want to solve your synthesis problem, and you'd like to use an automated reasoning tool for that. So if you have, in the controller synthesis example, too many inputs, then you can't even write down the encoding, right? So in that sense, of course, this is a bit simplified example, but if you can't even write down your encoding, how can you solve it, right? So in that sense, we care about succinctness, I would say. Okay, so quantified Boolean formulas are just propositional formulas where you have propositional variables. If you have a quantified Boolean formula, its negation is going to be a quantified Boolean formula. You can use the usual connectives, and then what's on top of propositional logic is that you can existentially or universally quantify. So you can say there exists propositional variable, and then QBF, right? So that's existential quantification. You also have universal quantification. Let me show you an example. So this, for instance, is a quantified Boolean formula, right? You say here, for all x, something, then here you have exists y, and then there are some propositional parts, right? And these things can be arbitrarily nested in principle. Here's another small example, right? I'm not particularly careful here with the scoping of quantifiers. I'll assume that always by using brackets in the right way, we can figure out which what's the scope of any given quantifier there, right? Okay, what are the semantics of these formulas? Well, we can think of them simply as succinctly written propositional formulas in the following way. If we have a QBF that starts with, or where we have a universal quantifier in this outermost position, then this is the equivalent to a conjunction of two QBFs. One where I substitute false for the variable that's quantified here, which is x, and another formula where, where I substitute true for my variable x. Okay, and the usual technicalities. It may be the case that you have a for all x in there in the subformula somewhere, and then of course it's like a different occurrence of that quantification, and then you don't replace it. You only replace the free occurrences. We can always assume just for convenience that all our, whenever we quantify over a variable, all the variables we quantify over are different, right? Okay, so that's for universal quantification. And then for existential quantification, that's an abbreviation for a disjunction, right? So again, you substitute false once, you substitute true, and then you take the disjunction of these two formulas. In that way, you can take any quantified Boolean formula, and by expanding, as it is called, I guess Shannon expansion is a common name for this, you will arrive at an equivalent propositional formula. But because of this copying of the phi here, in the worst case, you can get an exponentially larger propositional formula if you do that. Okay, just to apply this here, let's start with this quantifier here. This exists y. We can replace this by this disjunction here, right? We substitute false for y over here. Really use this pointer here. Substitute true here. And then we can simplify that a bit because I guess what do we get false here. So this will become true. And this will become, okay, so it will become true or z, which is true, right? Okay, and then we're left with this. So let's expand this existential quantifier. And we get this expression here. And again, we can simplify. So we have not true here, that's false. And that not false here, that's true. Oh, wait, sorry. Yeah. So we have x and true here, which could be x. And so at the very end, we have just for all x left. And that is false, right? Because it's just false and true. Okay, so by expanding in this way, you can always transform a quantified Boolean formula into an equivalent propositional formula. And some solvers actually do that, albeit in a clever way. Okay, so I've now introduced the most, general syntactic form of quantified Boolean formulas in practice. We typically assume that we get a normal form, which is Brinek's normal form, where all of your quantifiers are at the beginning in what's called the quantifier prefix. So the qi here are for all or exists. And yeah, the xi are the variables. and then you have a purely propositional formula phi, which is called the matrix, right? So you're assuming you have all the quantifiers at the beginning of the formula, and let me try and convince you that you can always transform an arbitrary QBF into in that format. If you have QBF that looks like this, where you apply existential quantifier just to phi, and then you have a connective and an OR here, then you can sort of, and assuming that your psi doesn't contain X free, then you can just sort of apply the quantifier to both of these formulas, right? And sort of pull out this existential quantifier to the top level. You can do the same thing for universal quantifiers, just the same condition is required. And then if you have not for all x phi, you can push the negation in. You just flip the quantifier from for all to exists, right? So not for all x phi is the same as exist x phi. Yeah? Negation phi, sorry, yeah, my mistake. So I think the same mistake is repeated here. Yeah, you would push the negation here. Sorry about that. Okay, so we're assuming for the remainder of the talk that we have Phoenix normal form. Depending on what your propositional connectives are, this is not maybe a bit more complicated than I just showed, but it's a simplifying assumption that we typically make in solver design. So you have a quantifier prefix, and you have a propositional matrix. And then we also typically assume that the formula is closed, so there are no free variables. Every variable that appears in this propositional formula phi is quantified over, right? So that in the end, this is equivalent to a truth value, false or true. Okay, so we can now define the first simple algorithm, which is like a very basic form of DPLL for quantified Boolean formulas. This you can alternatively understand this, interpret this as a definition of the semantics for Phoenix form QBF. So let's say we have, so this is this procedure evaluate here. We have a quantifier prefix. Let's assume this is some sort of list, and then the matrix. If the quantifier prefix is empty, then we've substituted truth values for all our variables. So we have some expression just over truth values. We can simplify that and get true or false, right? And we can return that as the result of this algorithm. If we have an existential quantifier at the beginning here, if Q1 is an existential quantifier, then we can recursively call the algorithm. One recursive call substitutes true for x1 for a first variable, takes the remaining quantifier prefix starting from x2, and the second call substitutes false for x1, right? And then if one of these comes back true, we can say true at the top level. And similarly for universal quantifiers, we again have two recursive subcalls, and if both of them come back true, then the QBF is true. Okay, so that's a very basic. I don't even want to call this DPLL, but it's a simple evaluation algorithm for quantified Boolean formulas in Phoenix normal form. Okay, what this also implies is that evaluating quantified Boolean formulas, this problem is sometimes called QSAT. And when the QBF is true, we say it's satisfiable, although sometimes the first order people will say, well, you don't really have a model. What are you talking about? So I sometimes say true and satisfiable interchangeably, or false and unsatisfiable. Okay. So if you look at this simple algorithm here, how much space does it need, right? So what we have to remember in each recursive, as we recurse into these subcalls here, is the assignments of our variables, right? The the x1 assignment here, and then as we go further down, the other assignments. So on the stack, we're going to have essentially just the assignments of the variables, and the depth of the recursion tree is n if n is the number of variables, right? So, okay, give or take a couple of constants here. We only need space. It's polynomial in the size of the input. So QBF evaluation is certainly in P space. Another way of understanding the semantics of quantified Boolean formulas, which is very useful, in addition to recursive evaluation and expansion, is in terms of a game. So now here I'm writing this a little bit differently. I now use capital variables here, by which I want to indicate that these are now sets of variables. This is a notation you also frequently see in papers. Instead of writing out a sequence of universal quantifier variable, you just group them into a single set called a quantifier block. And then, as you will see or as you can, we'll be able to see in a minute, the order within a quantifier block doesn't really matter. So we can just write them as sets. Okay, so now if I'm writing a QBF like this with this quantifier prefix where you have quantifier blocks and a matrix, then I can understand this in terms of a game played between an existential player, universal player. And these players take turns assigning their respective quantifier blocks. So the universal player would start here by choosing an assignment, Boolean assignment, variable assignment of the variables in U1. Let's call it tau1. Then the existential player, based on that, would pick an assignment of the variables E1. Then universal picks an assignment of variables in U2. Get it here. And so on, until all variables are assigned, right? We're assuming that the formula is closed. So at this point, we have an assignment for all the variables occurring in the propositional matrix phi. And so it'll evaluate to true or false. If it evaluates to true, then the existential player wins. And if it evaluates to false, the universal player wins. Okay, so this is for an individual play of this game. And then we say that QBF is true if the existential player has a winning strategy, right? So for any possible move that the universal or sequence of moves that the universal player can make, the existential knows how to assign their variables so that in the end, the assignment that comes out will satisfy the matrix. Or in the other case, because this game is determined, that there's always either universal or existential wins. In the other case, the universal player has a winning strategy. So regardless of how the existential player assigns their variables, they'll be able to assign their variables in such a way as to falsify the matrix. Okay. Good. Now, just a brief sketch explaining or trying to convince you that QSAT, QBF evaluation, is indeed P-space hard. So imagine you have a Turing machine. Your tape cells contain 0, 1, and your Turing machine is in a certain state S, and it reads a certain symbol, right? And we're looking at, we want to prove P-space hardness, so we want to say that if there's a polynomial bound on the space that the Turing machine uses, we can sort of capture whether the machine can accept by writing down a small QBF. Okay, so we have some polynomial bound on the space that the Turing machine can use. And I'm just saying, okay, we can have a propositional encoding that's roughly, in the size of Pn or some order of Pn that captures the current state of the tape and where the Turing machine is, right? What symbol it reads currently. So the configuration of the Turing machine. And the set of variables that we're using for that is X. And then if we have another set of variables that captures the configuration, let's call that Y, then we can write down a propositional formula if we sit down and actually do the work. That's true if and only if the Turing machine, it's possible to go from the configuration at the top to this configuration, right? We know what the Turing machine can do, and so we'll be able to write down such a formula, okay? Good. Now we want to define another formula which uses these sets of variables that says, okay, well, that's true if and only if I can reach the configuration encoded by X. No, sorry, if I can reach the configuration encoded by Y from the configuration encoded in X in at most one step. Okay, so what could that look like? Well, either X and Y are the same, then I'm already there, or I can transition from X to Y, right? Now, how would I, assuming that I have a formula for reach N, so in N steps, I can go from the configuration encoded by X to the configuration encoded by Y. How do I get one for 2N? Well, I can say there has to be some point in the middle, some configuration in the middle, Z, and I can go from X to Z, and then from Z to Y, right? So this is one way of defining that I can reach configuration Y from X in 2N steps, given that I have an encoding for reach N. The problem with that is that now I've copied this formula, right? I have two copies of this reach N formula. And so I would, as I go from N to 2N, I would increase the size of the formula by a factor of 2. And now we can use universal quantification to avoid that. And can do that by simply saying there has to be this midpoint, so that for all AB, well, either A is this initial point and B is the middle part, or A is the middle part and B is the end point. In both of these cases, we want there to be a transition from A to B, right? So we can just use universal quantification in this case to come up with an equivalent formula that avoids copying this transition relation. And here now, if we look at this formula, all of this depends just on Pn, right? We add some constant, Pn, a constant number of times as we go from N to 2N. And so we're able to express the whole thing here. So we can write down reach for 2 to the size of X. So if X is the set of variables that encodes our configuration, right? How many configurations are there? Well, at most, we can, at most 2 to the size of X, right? These are all possible configurations. Now we're asking, is there some path from an initial state of the Turing machine to an accepting state of the Turing machine? And the number of configurations that we can go through is at most 2 to the number of variables that we need to encode a configuration. And because this here uses this abbreviation here, we can write down this part here in a formula that's, well, I'm going to say linear in the size of in Pn, or in any case polynomial, right? So we can encode whether a polynomially space-bounded non-deterministic machine has an accepting run in a small succinct QBF. So that's why QSAT is p-space hard. Okay, so that was just the sort of the intro, syntax, semantics. Now we can get to the more interesting part, which is about algorithms for QSAT, for QBF evaluation. And whereas, in SAT, CDCL reigns supreme, in QBF, it's a little bit unclear what the best paradigm is. And I think there's still a lot of room for experimentation, for tinkering, and getting a decent QBF solver if you have a good idea. In SAT, your best chance is to take Alex's or Armin solvers, hack them a little bit, hope that you get some improvements on this year's benchmarks. In QBF, there's really room for you to come up with your own idea, implement it reasonably well, and get a competitive solve. Okay, so one more simplifying assumption for this next part is that our matrix is in CNF. That's an assumption that's common in SAT. In SAT, it's typically completely unproblematic. In QBF, not so much so, but let me just first try and convince you that you can always transform a Greenix normal form QBF into one that's even Greenix conjunctive normal form. And for that, you just use Zeitian transformation. So if your phi here uses AND gates, OR gates, and negation, you introduce new auxiliary variables that have to have exactly the values that these gates have under an assignment of the variables in the prefix. So if you have an AND gate with inputs x and y, you can introduce a new auxiliary variable z, and then you can add some clauses that ensure that z always takes the value of x and y. So here, let me see. So if x is false, then this becomes a unit clause, not z. So z has to be false, right? So if x is false, z is false. Similarly, for y, this clause says if y is false, then z is false. And finally, if x is true, then this literal disappears. If y is true, this literal disappears. And then we end up with a unit clause z, so z has to be true, right? So that way you can introduce a new variable z and some extra clauses that make sure that z always takes the value of that gate. You can do something similar for OR gates. Let's go through that. In this case, if x is true, then this part vanishes, right? This literal becomes false, and we end up with a unit clause z, so z has to be true, right? So if x is true, z is true. Similarly, this clause says if y is true, z has to be true. And finally, if both x and y are false, this ends up as a unit clause, and so z has to be false. Normally, you would, so here, negation is very simple. You just need these two clauses. And normally, you would just roll that into the gate definition for OR and 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 just work with literals instead of variables. But you can also do it like that. Okay. So given any circuit or any general matrix, propositional matrix, I can add these extra variables and clauses and get a CNF formula so that for any satisfying assignment of the original formula, I have a unique extension to these clauses to get a satisfying assignment. Okay. Now, one thing remains and that's where do we put these variables in the quantifier prefix? We have all these z variables now that we needed for the gates. And one safe way of introducing these variables to the quantifier prefix is just introducing them at the very end, right? So that's one way of doing it. There are some papers on, well, that are asking and kind of partially answering the question of whether that's always a great idea. You could also try and move them as far left in the quantifier prefix as possible. So in this case here, for x and y, sort of the leftmost you can go is just right of whichever of x and y is more to the right, right? So you need to be, the quantifier for z has to come after the quantifiers for x and y. And there's some interesting results on how that can affect the hardness of such of the formulas you get in the end. Right? But certainly a safe way of doing this is always introducing these existentially quantified variables at the very end. Okay, and psi now contains all of these clauses and is in CNF. And one thing that I might have forgotten is that you have some output gate in your original phi here, and then you have to add a unit clause in here that says the corresponding gate variable has to be true, right? Okay. So you can always transform your Prenix normal form QBF into one that's even Prenix conjunctive normal form. It turns out that if you do it that way, you're losing some information about the circuit structure, and that can actually be detrimental to solving. So I'm going to present an alternative way of doing this later, but just as a warning that CNF for QBF may not be the best idea. Conversion to CNF has disadvantages for solving quantified Boolean formulas. Okay, now let's get to the actual algorithms. So I think in the early 2000s, late 90s, people started to come up with versions of DPLL for quantified Boolean formulas. Because DPLL was well established for SAT, and there's a natural way of generalizing this algorithm to quantified Boolean formulas in Prenix normal form. Okay. And we already had like the basic version of this on an earlier slide, which is just this recursive evaluation algorithm. You can also make that iterative so that it's more efficient in some sense, but that's the initial version. And now we can try and improve that in various ways. So let's make a couple of observations, and this is what people did in. Sorry, I'm a bit sloppy with references here. I think after the presentation, I'll add kind of a bibliography at the end that tells you where to find the original papers in each case. So, okay, very basic observation. If I only have existential quantifiers, then it's an instance of SAT. And I can just call my SAT solver to figure out the truth value of this formula. Pretty trivial, but not a bad idea to do. Okay, another thing is can sort of approximate your QBF by deleting all universally quantified literals. So if you have a universally quantified variable and you have some clause, and that universally quantified variable occurs negated or unnegated, you could just remove it. And this is kind of a worst case assumption, like all of your universally quantified literal occurrences are false. And if even under these circumstances, sort of the worst case from the perspective of the existential player, if even in that case, you can just satisfy the remaining part by some truth assignment, well, then that same truth assignment will always be a winning strategy for the original QBF. So if that's satisfiable, then you can immediately answer, okay, my formula is true. Okay, so we can add, I'm going to call this subroutine apply SAT rules. You can add that at the beginning of your recursive evaluation algorithm to sometimes shortcut the algorithm and immediately give you a result. What else can we say? If we have an existentially quantified variable that only occurs positively, so x here never occurs as not x in a clause, then as an existential player, we can simply assign that variable true, and we'll never regret this, right? So in that case, we can just fix the value of x to true. And similarly, if x only occurs as not x, we can just assign it false, and we'll never regret this, right? That's what's called, well, the pure literal rule. And we can do something similar for universally quantified variables, only that now we're trying to make the formula false. So if x only occurs as x, we want to set that to false. And if it only occurs as not x, we're going to set it to true so as to make the literal disappear from the clause. Okay, so this is called, these are called pure literals. And you can add that to your routine, and what can happen is that once you apply this pure literal rule, you get rid of some clauses, and then another literal becomes pure, right? You can do that in a loop in order to successively simplify your formula. You can do until you can't make any more simplifications. So this is just, saying as long as your quantifier prefix keeps changing, or as long as you're making progress by assigning pure literals, we're going to do this, right? And then if you have no more pure literals, you just go to the recursive calls. Now, another rule that's QBF specific is a case where a clause only contains universally quantified variables. In that case, you can simply assign all of these literals to false as the universal player and just win the game, right? Because you falsified a clause, all clauses have to be satisfied. So in that case, the universal player wins, and the QBF is therefore false. And that's a very basic case of something that applies more generally, and it's called universal reduction. And that's a rule that works as follows. You assume you have a clause that contains a literal xi, or it could be not xi. That's really irrelevant here. And this is a universally quantified variable, the xi. And then all of the variables that occur in C are to the left of variable xi in the quantifier prefix. Just written in symbols here. All of the other variables, remaining variables in that clause, come before xi in the quantifier prefix. In that case, you can just remove that literal xi and add the clause C. You just remove that literal from your clause, add it to your formula, and still has to be satisfied. Why is that? Let me try and sketch a proof here. So assume you have an existential winning strategy, right? So the existential player has a way of assigning their variables so that regardless of what the universal player does, they will always satisfy the matrix. Okay, so given any universal play, which now is just a plain assignment of the variables, the response of the existential player in combination with this assignment tau will satisfy the matrix, right? Okay, so now I'm going to argue that that same strategy, that strategy F, actually also is going to work when you add C, when you add this reduced clause. And why is that? Suppose the universal player, has a play so that the play in combination with the existential response falsifies that more restrictive clause C. Then we can define a different play for the universal where we just make sure that xi, this universally quantified variable here, is assigned false. Or if the literal here is not x, then we make sure that the universal player here in tau prime assigns true, so that the literal disappears, right? Okay, so now we can look at the combination of that play tau prime with the response of the existential player. And because of this restriction here, so what we've done is we've flipped the value of xi in tau prime, right? We've changed that, possibly changed that value. But all the variables in C, we assumed to be left of xi in the quantifier prefix, okay? And so because the strategy can only take into account what has already happened, this play tau prime is going to be the same for these variables in C as for tau, right? None of that changed. So these responses must also agree on all of these variables, right? Because the first thing that changed was the assignment of xi, and the existential player can only react to that afterwards. Okay, so in fact, if this combined play pi falsifies C, then pi prime would falsify the original clause. But we assumed that F is a winning strategy for the existential player, right? So that's a contradiction. Again, the idea is that we assume that our more restrictive clause C, the one that we applied universal reduction to, that's falsified by a play. And then we modify the value of xi in that play, get a new play, and we can observe that actually the response of the existential player still has to be the same on the relevant variables. So that strategy that we had originally that was a winning strategy actually also has to work for C. So applying universal reduction is sound. Okay. So we can also add applications of universal reduction to our simplification rules for quantified DPLL, right? So yeah, we add that in our loop, and we can get synergetic effects from applying both pure literal reduction and the pure literal rule and universal reduction. Okay, and finally, the most important thing in SAT, unit clauses. Well, we can also have that can also use that in QBF, right? If I have a clause that contains an existentially quantified variable or literal here, then we have to assign that true. Otherwise, the matrix will be falsified. And that can lead to further simplification. Yeah, and that's I think that's the QDPLL algorithm as it was initially defined. Any questions about this part? I have what, 25 more minutes? Okay, great. Just like in SAT, where DPLL was superseded by CTCL, by conflict-driven clause learning, there is a way of turning DPLL into a clause learning style algorithm for quantified Boolean formulas. So let's start with a quick recap of CTCL for SAT. So in this algorithm, we do something in a loop, like an infinite loop, until we terminate. We propagate unit clauses. By doing that, we will either, we'll either be done at some point or we'll falsify a clause. That's what we call a conflict. So, and if there is a conflict, then we perform conflict analysis to get a new learned clause and a backtrack level. If the clause we learn is empty, well, then the propositional formula, because the clauses we learn are implied, had to have been unsatisfiable. Okay, I'm saying false here. Otherwise, we add our clause to our database, make sure that it's unit propagated and everything, and we backtrack. And then, so if we're in that branch here, afterwards we go back to unit propagation, right? And by unit propagation, we'll flip some variable assignment and continue. Now, If there's no conflict detected and we've assigned all variables in SAT, well, we know we're good, right? We've assigned all variables. No clause is falsified, so must have a satisfying assignment. In that case, we say true or satisfiable. And the remaining cases that we don't have a conflict, but we haven't assigned all variables yet, so we let our decision heuristic give us a variable, and we'll assign that variable. Okay, so quick example here. With these 4 clauses, there's no unit clause, so we start by a decision, start with a decision, and we may assign x true. Okay, then this clause here, which is, sorry, up here, yeah, there it is. That becomes a unit clause, so we have to set y true. And then this clause here is falsified, right? Okay. Now we perform clause learning, so we look at this clause that was falsified, and we ask, okay, what was the last variable that was assigned, or last literal that was assigned false? Let's find the clause that by unit propagation forced us to make that assignment, and then let's apply the resolution rule to these 2 clauses. And here we get a unit clause, not x, which is an asserting clause, as Artix mentioned earlier. So it's a clause that will cause us to flip a variable, right? So in particular, we've made this decision to assign x true, and now the learn clause will force us to assign x false. So we're making some progress here. Okay. We now have that clause in our database. We'll backtrack to decision level 0, and we'll assign the variable false. Okay. If we do that, then this clause here, x or y becomes unit. Again, we have to assign y true. And now we have a conflict with this clause. So this clause is falsified. Again, we perform clause learning. We resolve these 2 clauses. We get x as a unit clause, and now we can resolve with not x to derive the empty clause and conclude that the formula is unsatisfiable. Okay. That's CDCL for SAT. How can we make that work for QBF? Well, we're going to have to make a couple of alterations, actually. One is we have to decide what kind of propagation or what analog of unit propagation we're going to pick for QBF. Then conflict analysis is going to have to change a little bit. We're going to have to use a different proof system. Then there's something, okay, obviously we need to do something for the case when we find a satisfying assignment. Because while in SAT, once we have a satisfying assignment, we're done. Now, because we have these universally quantified variables, well, from the perspective of the universal player, maybe they can play in a different way, right? We have to learn something for the universal player that ensures that we really explored all possible plays for them. We can't just stop at this point. And finally, as I'll show you later, we will have to make maybe some restrictions on a decision heuristic because problems can arise if we do that in an unrestricted way. But I have an extra slide on that. Okay, so one suggestion here, and that's actually not the canonical way, but I think for our purposes, maybe a good start, is to just propagate existential unit clauses. And once we find a clause that, after propagating, only contains universally quantified variables, we say, okay, we stop. Now we found a conflict, because at that point, certainly if we have as we already argued, if we have a clause that only contains universally quantified variables, that clause can be falsified by the universal player. Okay. Then we have some form of conflict analysis. I'll go into detail in a moment. Okay. And then we have something for the case where all variables are assigned, where we will kind of generate a conflict from the perspective of the universal player in a certain way. And then go to conflict analysis. Okay. I think maybe normally you could avoid the go to. Here I'm using it just to keep the pseudocode relatively simple. And what's the remaining case? Well, the remaining case is you've propagated. but you haven't assigned all variables, then we'll again make a decision, like just like in CDCL. Okay. And here I'm going to make a restriction or apply a restriction. We may only choose an unassigned variable for a decision which comes from the leftmost block of variables, quantifier block that has unassigned variables. So when we're assigning variables, we're assuming we just remove them from the quantifier block. And then maybe because of that, some quantifier blocks may be merged. But in any case, we're going to have some quantifier prefix after simplification. And we're going to choose an unassigned variable from the leftmost block that has unassigned variables here. Okay, so that's the kind of the standard way of doing that. Okay, let's see a simple example where this works out. Okay, so we now have a universally quantified variable u in the middle here. So sorry, here I just used commas. What I mean is E1 and E2 are both existentially quantified, right? And similarly for E3 and E4. Okay, and what are our clauses? These are our clauses. So in this case, we don't have any unit clauses. There's nothing. Yes? All the variables occurring in a clause. Okay, so we have a set of variables occurring in a clause.
Yeah.
And the corresponding variables are all quantified with for all.
Okay, so do you mean like all the variables are quantified universally, and inside you have a propositional formula in some CNF?
Yes.
Yes.
Well,
So what if the CNF is a tautology?
Sorry?
A valid.
So I'm just sorry, no, I'm just talking about an individual clause. Right?
Okay.
Which is part of this.
Okay.
So after assigning some variables, we end up with a clause that could be smaller and that now only contains variables that are universally quantified.
Okay.
Just a single clause.
Okay. Thank you.
And that, then that is false, right? That can be made false by the universal. So it's a kind of the conflict analog for SAT. So these are our clauses. And as you can see, there is no unit clause, nothing to do for propagation. So, and we haven't assigned any variables. So we end up over here and we have to decide a variable. And we also have to conform to that restriction. So let's pick E1 here and assign that true as our decision. So then we indeed have some propagation. So this clause here becomes a unit clause. And we assign E for false. And now we have this clause up here, where E4 is false and U is universally quantified. We said that's where we're going to say we have a conflict. Oh, yeah. So now we want to perform conflict analysis. In SAT, that's done using propositional resolution. In QBF, we can use a very similar proof system called Q resolution, quantified resolution. And that consists of the propositional resolution rule. So if we have clauses C1 or X and not X or C2, then we can derive the clause C1 or C2. Because that rule is propositionally sound, it preserves all the assignments. In particular, it also works for QBF. And then we add universal reduction, right? We already saw what the rule is. If all variables in C come to the left of U, then we can remove this universally quantified literal from our. Okay, so that's the system that we're going to use for conflict analysis. Apart from that, we're going to do the same thing as in CDCL. So we start from the conflict clause, which here is U or E4. And we look at the last literal that was falsified here. That's E4. That had to have been propagated by another clause, which in this case is this clause. And so we can apply the resolution rule with pivot variable E4. We can derive this clause, not E1 or U. Okay. And now let's take a look. E1 is left of u in the quantifier prefix, right? So we can apply this universal reduction rule, remove u from that clause, and just derive the clause, not E1. And intuitively, just like in SAT, that clause is one that we can use to tell us that the decision we made was wrong, right? So we can backtrack, undo that decision, and by unit propagation, this clause here will force us to instead assign E1 false. Okay, so let's do that. We now have not E1 in our clause database, and by unit propagation, we set E1 to false. Then get another unit clause here, set E3 to false. Okay, then this clause here becomes a unit clause where we have to assign E2 true. And let's see, E3 is false, E2 is true. And then therefore we now have a clause here that only contains a universally quantified literal, not U. Okay, so we again apply conflict analysis, use Q resolution to derive the clause, not U or E3. Now notice we can't apply universal reduction here because E3 comes after U in the quantifier prefix. So we have to continue resolving, find the reason, the clause that is responsible for assigning E3 true, E3 false, which is this one. We derive E1 or not U. Now we can apply universal reduction to derive E1, and then finally resolve these two unit clauses to derive the empty clause. Okay, so what we've done is we've constructed a derivation of the empty clause from the matrix using Q resolution. And because Q resolution is a sound system, well, it didn't prove that, but I just claimed that. Because it's a sound system, that means that the original formula had to have been false or unsatisfiable. Okay, so that's a way in which we can, that's a run of quantified CDCL, which just uses the clauses and where everything just works out. Now let's see what we have to do when we get to a satisfying assignment. So slightly different example now. New set of clauses, but again, there's no unit clause, so we start with a decision. In this case, we assign U1 false. Then this becomes a unit clause. We assign E1 false as well. And then I think that's it, right? So no conflict. We just propagated a few, propagated E1 false. So we make another decision, assign. Okay, now let's see. So E1 is assigned, E1 is assigned. Next quantifier block that has unassigned variables is just this U2 variable here. So we make a decision on U2, assign that false. Then here we now have a clause that becomes unit where we have to assign E2 true. And I think again we're done. But now actually what we can, now we've assigned all variables, right? We're in that branch where we've propagated. Now we've assigned all variables, nothing to propagate. And that means we have a satisfying assignment. And that's the satisfying assignment, right? So this is an assignment that satisfies our matrix. And now in order to perform conflict analysis, we just use the exact dual system to Q resolution. So this is a conjunction of literals that's sometimes called a cube. And now our resolution system or consensus system, as it's sometimes called, so that's getting ahead of myself. So this, coming up with this initial cube here that is a satisfying assignment, that's called model generation, okay? And now as a proof system for conflict analysis, we use the dual of Q resolution, which is called Q consensus. And the rules are, well, this is essentially resolution. You just flip, you just flip ORs. Instead of ORs, you have ANDs now. So that's one rule. And then you have, instead of universal reduction, you have existential reduction. But it works the same way. So if you have an existentially quantified literal, so that all other variables here in this term or cube t come to the left of e, then you can just remove e. Okay, derive t. And so now we perform conflict analysis by applying existential reduction and resolution. And in this case, we only have so far, we only have that cube. Oh, yes, question. Sorry, I think the mic's not on.
In the proof system, your goal is to get to the empty clause. What is the goal here?
Okay, so here the goal is to get to the empty term. So that would be an empty conjunction, which is trivially true. So if the set of terms that we derive are implied by our, or rather imply the matrix, right? So this here implies our matrix phi, right? So if this is true, then the CNF is satisfied. Now, if we have a set of such terms from which we can derive the empty term by Q consensus, then the QBF is true. So yeah, it's kind of the dual goal. Try and derive as small a term as possible. And if you derive the empty term, then your QBF is true. We didn't prove that that's the case, but you just have to trust me on that. Okay, so now we have this first term here. We can't really do much with that. The only thing we can do is apply existential reduction, get rid of the E2 to derive that term. And that will be good enough to just undo that assignment of U2 false. So, okay, well, we also need, I'm not sure I'm saying this. So once we have terms, we also have to propagate them, right? And the right way to propagate them is to, if we have a term that only contains one universally quantified literal, that literal has to be falsified in order to not satisfy the term. So everything's kind of flipped around a little bit. But if you sit down and think about it, you can realize it's okay. Do we have a notion? Yes.
Once you have a satisfying assignment, if you had a way to turn some values into donkers.
Ah, yeah,
that would be
excellent
helpful,
question.
right?
Okay, yeah, great question. So I think that is actually, I think one of the main reasons why QCDCL has problems, that we end up deriving or getting the initial terms that are very large. So yeah, we would love to have better ways. I think there are ways, right? I haven't really looked into this,
Yeah,
but
yeah. I mean, we have a paper at the main conference about generalization.
Yeah.
So how you kind of can replace values by donkers.
okay, great. No, and I know there's been a bit of work on kind of DNF generation lately that I think could be applied here. Perfect, yeah. So the naive way of doing it is just getting this initial, or the most basic version is just take the full assignment. Sometimes you can be a bit more efficient. I think it actually would pay off greatly if you can turn some values into don't cares and remove them from this initial term. Okay. I mean, if you have a don't care, you just remove it from your term, right? Ah, okay.
Then it's fine.
Yeah. Ah, okay. Here.
Exist C1 for all U1, exist C2 for all U2. Then I'm not sure about the U2 over there because, right? And basically the for alls you want to replace by don't cares, right?
Either, right? I mean, what we want is as small a term as possible. Yeah, I mean, the specifics of how to do this, I think, or how we can use that are a bit tricky. But yeah, that would be the goal. Come up with small terms. Yeah.
The order would matter, right? Which you want to get rid of your Boolean values.
Yes, I guess that would have to factor in somehow the quantifier, the order of quantifiers. Yes. Yeah, sure. If that, yeah. Mm-hmm. Okay, just real quick, I think maybe, yeah, I think 2 minutes. So we have terms now. We also propagate these terms. And so here we now have a term that, okay, U1 is false, so this is true. So in this term, which is a conjunction, this literal would just disappear. E1 is false, so this literal will also disappear. So we're just left with not U2. And so if U2 is, or if it's not U2, literal is true, then the entire term is true, which means that the extensional player has a way of winning from this partial assignment. And so as the universal player, I have to make sure I falsify that last literal. So here, U2 will be assigned rule, right? So yes, in that case, that term will be falsified, and that's how we want to propagate from the perspective of the universal player. Okay, so we've undone that assignment. Then immediately after that assignment, we get another satisfying assignment by model generation. Now we can actually apply a consensus step, derive this term. We can apply existential reduction and derive not U1 and go all the way back to and undo that decision here. Okay. And then starting with this unit term, we proceed as before. So now we assign U1 true. Remember, we want to falsify terms. And then we get some propagation from assigning that universal variable. We get propagation, unit propagation on clauses. So we have to assign E1 true here. And that's it. Then we've propagated everything, no conflict, no, we haven't satisfied the matrix. So we make another decision. We to go through this more quickly. Okay, if we assign U2 false here, we get another initial term. Oops, what did I do there? Oh yeah, so we add this term, propagate this term, and now, okay, we get another satisfying assignment term, and then we can apply existential reduction, resolve these two terms to get the term U1 and E1, apply existential reduction. We end up with the unit term U1, and we can use Q consensus on these two to derive the empty term. So we've derived the empty term using Q consensus, and therefore the QBF is true. Okay. Yeah, and I think that's a great, yeah, I think the session is over, right?
Just one announcement, or maybe a couple of announcements. One is, of course, regarding the use of mics. Because there are online participants, it might be useful that when you ask a question, you just ask it on the mic so that they can hear too. Okay, and it also gets recorded. The second thing is, because there are some of us, I mean, you probably, I don't know whether you would be there tomorrow. You would be there. Okay.